Hello everyone and welcome back. Today in this video we are going to be looking at generating a complete graph of the following function here, x plus cosine x. And we're going to be putting together basically everything from Unit 5 in this one. Before you start jumping into the calculus, we want to take note of the domain, okay? And in this one, cosine is defined everywhere. X is a polynomial is defined everywhere. Our domain here is negative infinity to infinity. Okay. So then, we need to know what's actually happening as x approaches plus or minus infinity. And that's kind of the point of knowing the domain. If there's a restriction, we want to find the limit as x approaches that restriction from the left and from the right to see what's happening. Otherwise, we either need to find out what's happening at the endpoints, or in the case of a domain involving negative infinity to infinity, we want to evaluate the limits as x approaches plus or minus infinity. So let's do negative infinity first. X plus cosine x. Okay. Let's think about this. So the function x. Let's just think about what the function x is doing. And I will, make a little tiny graph here. And the function x, as x approaches negative infinity, the function x is this guy. As x goes to negative infinity, the function x, the y value here, is just going to approach negative infinity. Okay? So nothing too crazy happening there. And the function cosine, hopefully we remember that cosine is just a wave that oscillates up and down between -1 and 1. Okay? So, in other words, this whole thing is going to tend toward negative infinity. Okay? Because, again, this one goes to negative infinity. This one, worst case scenario, is +1. Negative infinity plus 1 is negative infinity. Okay? And similarly, the limit as x approaches plus infinity of x plus cosine. Same kind of thing. Think about this graph. This graph is darting off to infinity. And this thing is going between -1 and 1. So therefore, the whole thing is going to go to infinity. Okay. There we go. Okay. We also want to think about intercepts. Okay, so x-intercept. Let's remember that's where y is going to be 0. So in other words, we get x plus cosine x. We set that equal to 0. And, we get this situation here where cosine x equals negative x. And, yeah, this equation, not necessarily the easiest to solve. We might come back to this later. But this one, because it has a polynomial and a trig, it's pretty hard to solve. But we might be able to use some information later on to figure out what this is. We're just going to keep this here like this for now. And let's do the y-intercept, right? That's got to be easier, yeah? Y-intercept is going to happen when x is 0. Okay, so if I do f of 0, I'm just going to get 0 plus cosine of 0, and hopefully we all remember what the cosine of 0 is, yeah? Cosine of 0 is going to be 1. So we get 0, 1. Sorry about that, everybody. 0, 1 is a point on the graph. The point 0, 1 is on the graph of f. Okay. All right. Now, let's jump in to some calculus. Okay. So what we are going to look at is, first of all, let me just write this function down again. x plus cosine. All right. So we're going to look for maxes and mins. Okay. And so let's remember how we do that, right? We're going to look for where our first derivative is either 0 or undefined. And this thing is undefined nowhere. So the only thing we really have to consider is where the first derivative is 0. So if I take the first derivative of this thing, the derivative of x is going to be 1. The derivative of cosine, it is a co-function, so it's going to be negative 1 minus sine x, and then we're going to set that equal to 0. Again, because these functions are defined everywhere, so we don't have to consider the undefined case. All right. So now if I solve this thing, 1 minus sine x equals 0, this is a linear, so I want to get my trig on one side, add sine x to both sides to get sine x equals 1. And now I'm back in pre-calculus mode. I gotta think about what angle or angles have a sine of 1. And hopefully we're all okay with the idea that there's only one angle. And that is that one right there. That's going to be 90 degrees. Okay. It's 90 degrees, and in radians, that's going to be good old pi over 2. Okay, so x is going to equal good old pi over 2 plus 2 pi k. And of course, k can be any integer in the world. Okay. All right. So these are what are called our critical numbers. Critical numbers for extrema. Okay. Pi over 2 plus 2 pi k. All right. So now let's see what's happening, right? Let's start k off at 0. Okay. So we're going to start k off at 0. In that case, x sub 0 is going to be just pi over 2. All right. Now the idea here is that the slope is exactly 0 at pi over 2. But we don't know, okay, either this is happening or this is happening. We need to figure out which one's which. Okay. Do we have a max or do we have a min? And that's what we're going to go through right now. Okay, now we have got to be careful because there's literally an infinite number of critical numbers because this integer can be anything. Okay, so what I'm actually going to do is I'm actually going to write down a few of these. Okay, so I'm going to write down k equals -1. So that's going to give me x sub -1 equals, and that's going to be pi over 2 minus 2 pi. Okay. And pi over 2 minus 2 pi, that's going to be minus 3 pi over 2. I'm going to do k equals -2. It's going to give me x sub -2 equals pi over 2 minus 4 pi. Okay. And this is going to give me, let me think, what's this going to be? 1 minus 8, -7. -7 pi over 2. Okay, and now let's go the other way. Let's do k equals +1 because we're just trying to establish a pattern here. Okay, k equals +1. We're going to have x sub 1 equals, it's going to be pi over 2 plus 2 pi, right? Yeah, pi over 2 plus 2 pi, which is going to be 5 pi over 2. And then finally, if k equals 2, then we're going to get x sub 2 equals pi over 2 plus 4 pi. Okay, and that's going to give us 9 pi over 2 is what that's going to give us. 9 pi over 2 there. Oh, right. Okay. So now we have a bunch of stuff that we have to check through. Let's see if we can establish a pattern here. I think we can. Okay. So anyway, let's go all the way from the left. So we're gonna go. Yeah, we want increasing, decreasing. So all these are gonna have parentheses. Um, so we're gonna do negative 7 pi/2 to negative 3 pi/2. We're going to do negative 3 pi/2 to pi/2. We're going to do pi/2 to 5 pi/2. And we're going to do 5 pi/2 to 9 pi/2. Okay. Now, what can we do? We just need to select anything in here. So let's make it easy, right? This is like minus 1.5 pi. This is like a, so let's just do minus 2 pi. That's in here. Negative 3 pi/2 to pi/2. Let's do 0. Pi/2. Let's do pi. You know, because this is like 2.5 pi. 2.5 pi. Let's do 3 pi. Okay. So these are the numbers that we're going to plug in, and we're going to see if our first derivative is positive or negative. Here's our first derivative right here. Okay. Now the sign of any pi is 0. Okay. So guess what? We have positive first derivative here. Sign of 0 is 0. So we have positive first derivative here. Let's see. Sign of pi. Sign of pi is 0. So we have positive first derivative here. And sine of 3 pi is 0. So we have positive first derivative here. I for some reason was not expecting all of this. What does this mean? What does this mean? The sign of the first derivative never changed, right? So that means that if the first derivative is positive, let's take a look, right? So first derivative is positive, first derivative is 0, first derivative is positive, first derivative is 0, first derivative is so this is what is happening with this function. Okay. So no change in sign. No change in sign for the first derivative. So therefore we have no extrema. And this tells us that the function has no turning points. And fancy mathematical word for this is it's monotonic. It only grows in one direction. It only travels in one direction. It only goes up. Okay, good. All right. Now let's see. We can see just from this graph, we can see that the concavity does change. Okay, so let's see if we can find where the concavity changes. Okay, so we're gonna do the same process but with the second derivative now. So here's my first derivative. Let me come over here and rewrite the first derivative. All right, so the first derivative, 1 minus sine x. I don't know why I said that equal to 0. And don't do that. Don't do what I just did. We're not setting it equal to 0. we are taking another derivative. That's what we're doing. All right, so this is how we find, remember, changes in concavities. This is what the last video was about. If I take the derivative of this, I just get 0. And then I just get minus cosine x equals 0. Okay. Well, this is easy to solve. I can just multiply both sides by -1, get cosine x equals 0. Let's remember that cosine is the x component of the r component. So they're equal to 0. That means we're looking for angles that have an x component of 0. Okay. So, you know, make a little sketchy boy if you want. And, you know, this angle, x is not 0. This angle, x is exactly 0. This angle, x is exactly 0. So the angles in question here is going to be pi over 2, but also 3 pi over 2. Okay, and one way that we can write that, we can combine that into one expression, pi over 2 plus pi k, where k is any integer. Okay, and just like we did before, we're going to make a few intervals, and we're going to see if the concavity changes. We're going to see if we can establish a pattern. Okay, so let's do the same thing we did before. Let's do k equals, let's do -2, -1, 0, 1, and 2. So if we do -2, pi over 2 minus 2 pi, well, it's like 1 minus 4. It's like -3 pi over 2. Pi over 2 minus pi over 2. Pi over 2 plus nothing. Pi over 2. Pi over 2 plus pi. 3 pi over 2. Pi over 2 plus 2 pi. 5 pi over 2. Right? Okay, so this gives us more intervals to check now. All right. We're just doing the same thing we were doing, just one more derivative. Okay. So there's that first interval. And again, the hope is that we can establish a pattern for what's happening everywhere by doing this. Okay. 3 pi over 2 to 5 pi over 2. And did I forget an interval? I think I did. Negative pi over 2 to pi over 2. Pi over 2 to 3 pi over 2. I forgot that one. All right. All right, good. So let's see what happens here. So we need a number to put in between these two values. So let's do, how about -pi? How about 0? Here, how about 4 pi over 2, which is the same thing as 2 pi? And here, how about 2 pi over 2, which is the same thing as pi? How about that? Right? We're going to plug this into the second derivative, okay? Second derivative, which we found to be, the second derivative is negative cosine, okay? So here we go. Negative cosine pi. Well, cosine pi, -1. Negative of that, definitely positive, okay? So that means our function is concave up on this interval. All right, once again, plugging this into the second derivative, cosine of 0 is going to be 1, and we have the negative of that, so that's going to be negative. We are concave down, ladies and gentlemen. Okay. 2 pi, if I plug in 2 pi, cosine 2 pi is going to be 1, but we have a negative there. And so that is going to be concave down, but this is the one we skipped. Remember, we skipped an interval there. So we actually going to go through this one first. Okay, cosine pi, -1, negative of that is positive. That means we're concave up. Okay, so so from left to right now, we go concave up, and then concave down, and then down here, concave up, concave down. So once again, here we are, and we have a pattern now. We're going to alternate concave up, concave down, concave up, concave down, and the concave up is going to happen. Well, hold on. Yeah, I'm sorry. Uh, each of these is going to be each of the intervals are going to be pi apart, and they're just going to alternate up, down, up, down, up, down, up, down. Okay, so this tells us what is going on pretty well. So now, can we get a good plot of what's going on with this information? Let's see if we can. Let me. Okay, let me come down here and let's make some graphs. Right, y-axis, x-axis. Right. Okay, and so what do we know? What do we know? Let's internalize all this. Okay, we know that the first derivative is always positive. Okay, so we know that. Um, with the okay, I'm sorry, with the exception of where the first derivative is 0, right? So every pi over 2, um, the first derivative is going to be 0. But everywhere else, the derivative is going to be positive. So we have this situation, something like this happening. Okay, um, but then if we look here, we are concave. We're opening down. If we were to continue this like this, we'd be opening down. So concave down, concave up, concave down, concave up, like that. Okay. So now we're just going to get more detailed about what's going on here. And what else do we know? We know that 0 comma something is a point on the graph. That was like one of the first. Yeah, 0 1. Okay. So let's come over here. 0 1 is definitely on the graph of f. Here's 0 1. Okay. And now we know. Look at these intervals for our second derivative now. Where's our second? There we go. Here's our blue boys. Negative pi over 2 to pi over 2. So from here to here, let's just say this is negative pi over 2 to pi over 2. We are concave. We are concave up. No, we're not. We're concave down from negative pi over 2 to pi over 2. Okay. So what is that going to look like? It's going to look, well, hold on. We're gonna do it, but let me make sure that I get the critical point as well. Okay. So our solution here, negative 3 pi over 2, pi over 2. Negative 3 pi over 2. Okay. So here at pi over 2, the first derivative is exactly 0. So right here, this, so somewhere here is where the slope is going to be flat. So here the slope is flat. And we know that we are concave down, which means our slope is getting more negative as we go. Yeah, so we kind of have a situation. This is really hard to draw. Really, really hard to draw. And if I can't replicate it, we're just going to go to Desmos. We're not going to sweat it. Here, the first derivative is exactly 0. And let's try this. Yeah. You know what? I can't draw it myself. But we can go to Desmos here. So let's do that. Okay. Okay, now where Desmos? All right, let's look at this graphic calculator here, and x plus cos x. Yeah, and this is going to illustrate what I was trying to illustrate. Let's see. Yeah. Okay. So, concave down. Look here, concave down. The slope is getting more negative. Okay, right here, pi over 2. Pi over 2 is like 1.57. Here's 2. Here's 1. 1.57 somewhere here. So as we can see here, here's where the first derivative is 0. Okay. And then we're concave up, and then we're concave down. Look. Let's go down here. We can kind of see it. We can see a little better because the shape repeats itself. Okay. First derivative is 0. Then we're concave up. Okay. But now look here. Here the slope is decreasing, so concave down. So the inflection point is about here. So this must be like negative whatever. Let me go back. Negative, like negative pi over 2, okay, or negative 3 pi over 2. That's negative 3 pi over 2. All right, negative 1.5 or whatever. Right there. That's where we go from getting more positive to getting more negative. Okay, so inflection point right about here. Critical point for the first derivative right here, but it doesn't change direction. So there's no extrema. It's just going to keep growing. This shape is just going to keep repeating itself forever and ever and ever, just like that. And we were able to determine this with our first and second derivative tests. All right. Nice. I want to call it